Okay. So, applications of the dot product. So, from yesterday, we learned an operation that is specifically just for vectors. Okay? You've never heard of a dot product before because you can't do a dot product to scalars. It's only for vectors. And we learned two definitions. We learned a geometric definition and an algebraic definition. I could have taught you the geometric definition in Unit 6, but we save it for this unit and do it all at once. So the geometric definition, if we have two vectors, do you guys want to call them A and B? Let's call them A and B. So we have vector A dotted with vector B. The geometric definition is the one with the magnitudes and angle in it. You remember what it was from yesterday, guys? Magnitude of the first vector times magnitude of the second vector, cosine, angle between. And again, for both of these, you have to kind of visualize that the angles are attached tail to tail. That's the picture that goes along with dot product. Attached vectors tail to tail. The theta is the angle between the vectors aligned tail to tail, and magnitude of A, magnitude of B are the lengths of the two vectors. And then we learned the algebraic definition of the dot product, which is using these new things we've learned called Cartesian vectors. Okay, and if you remember, a Cartesian vector is when you can write a vector in terms of its components or I'll say an x component and a y component. That's the pathway from tail to head. Okay, so so the references for this are, if you have that vector A is A1, A2, A1 comma A2, and vector B is B1 comma B2. So I'm just referencing the values that are in the vector, in the x component and y component spots. Okay, if that's what you have as vector A and B, then the dot product is, if you remember, you take the x coordinates and do what to them? The A1 and the B1, you multiply them. A1, B1. And then you add the product of the y coordinates. Sorry, yeah, A2, B2. And ta-da, you have another definition of dot product. And so, if you guys get that the geometric picture goes with like the first one, the algebraic vectors that look like that go with the second one. But they're both going to equal the same thing. You don't get different dot products, it'll be the same thing whether you use, depending on what inputs you use. So we're going to now, because the title of this lesson is Applications of Dot Product, we're going to learn how the dot product is used in different situations. So the first one we're going to do is work. So it's called work. Physics people should know about work. Okay? So work, okay, so work, all you need to know about work, it's the dot product of a force in newtons and a displacement in meters. So here's your formula for work. Work is the force dotted with the displacement. Okay? And the rule is that your answer of this is going to be in a unit called joules. Okay? Capital J. Okay? So let's read this scenario. It says, Angela has entered the wheelchair division of a marathon race. While training, she races her wheelchair up a 300-meter hill with a constant force of 500 newtons applied at an angle of 30 degrees to the surface of the hill. Find the work done by Angela to the nearest 100 joules. Okay. So work is the dot product of the force and the displacement. So you see a question, it says calculate the work. The first thing you should do is write work equals force vector dotted with displacement vector. And now you have to make a decision. What's the more appropriate choice of dot product formula to use for the question. In this case, looking at the way the information is provided, should I use the geometric or the algebraic definition? Yep.
Geometric.
Yep. So magnitude of force times magnitude of displacement, cosine angle between. Picture what, like in picture form, do you guys get that you have, the idea is, so you're going up a 300-meter hill, okay? So they're making life kind of weird. So like they're saying it's a hill, so I guess I'll make a hill. So here's a hill, okay? So we have that the Angela, two things are happening. So first of all, she is going to move 300 meters up this hill. Let me keep it here, okay? So if she's moving 300 meters up this hill, do we agree that her displacement is this green vector that I'm creating right here? And I know that that vector has a magnitude of 300 meters up a hill, okay? And then she's applying a force of applying a force at an angle of 30 degrees to the surface of the hill. Okay, so that she's not just, so there's an angle between the force and the displacement, right? Because when I don't know if you're thinking about, if you're in a wheelchair, when you're pushing, you're really using a motion that's kind of going on an angle like this to move forward. It's not like someone's pushing her up the hill and it's like just like right behind her. She's using her own like arms to push the wheels, and she has to push at an angle to make the wheels turn. Is this making sense? Okay. So where should the 30 degrees look like? Well, I guess you could technically say that from her perspective, the 30 degrees is working like kind of like this. Agreed? Like there's like a 30-degree angle kind of going downwards towards the hill. Does this make sense, what I just drew? Is the vector diagram I just drew, though, useful for dot product? Where should the angle end up being? The 30-degree angle is technically, isn't it basically that 30? Do you see like it's Z pattern? So even though, remember, it's all about the forces. So the 30 degrees, because again, this is like with the, think of it like that, right? Z pattern. So the angle that the force is making with the hill is a 30-degree angle. I've made life a lot harder for you. By going to the picture, I wanted to give you the visual, but usually for these work questions, it's literally just plug and shove, to be honest with you. But I wanted to just see the visual. But now that you have it, yep. Yeah, go on.
Alexa Huck Griffin, please report to the main office. Alexa Huck Griffin, please report to the main office. Thank you.
Do you have those three pieces of information? Are those all provided for you in the question? Do you know how big the force is in newtons? 500. Do you know what the displacement is? How far she travels in meters? Do we know the angle that the force makes with the displacement? And we type this into our calculator. 500 times 300 cosine 30. So 500 times 300 cosine 30. I got 129,904. Okay, joules. And then it says round to the nearest 100 joules. So we're just as a conclusion. So the work done by Angela is approximately, if I round that to the nearest 100 joules, 129,904 rounded to the nearest 100, 904 rounded to the nearest 100.
12,900.
129,000. Beauty. We found the work. Okay. Okay. And that is that one. So it's normally just a plug and chug situation for work. Okay. Moving on. Okay. Example 2. Love these ones. These ones are cool. So example 2. Finding an angle between two vectors. So determine the angle between the vectors in each pair to the nearest 10th. So I'm giving you an A. Vector G is 5, 1, and vector H is negative 3, 8. So I'm going to go back to this question for a second. In this case, there was no ambiguity of what the angle was. I give it to you, right? 30 degrees. Here, I don't have that. But I still do have two vectors. And the key here is going to be, if I want to find the angle, and I know dot product can be represented in both these ways, can you kind of see a way that perhaps you can create a formula that kind of incorporates both of these things? If both magnitude of A, magnitude of B, cosine theta, and A1, B1 plus A2, B2, if both of those distinct things equal the dot product, can't you just equal those two things together? And if you do that, if you equate the geometric to algebraic, we can easily do the algebraic one, because we have all the coordinates, just plug and chug. And then cos theta, I want the theta, that's the missing piece. The only other pieces are going to be a magnitude of A and magnitude of B. Did I teach you how to do that as well, to find a magnitude of a vector in algebraic form? So what ends up happening here is, so you end up with, so I'm going to do this in a few steps just so that everyone kind of sees it. We all agree that dot product equals dot product, which is the magnitude of A times the magnitude of B cosine theta is going to equal A1 B1 plus A2 B2. So cos theta will be A1 B1 plus A2 B2 all over magnitude of A times magnitude of B. And then you can cos theta, cos inverse, and tada. You will find the angle. Okay? So, instead of A and B, it's going to be G and H. So if I want to find the angle between vectors G and H, is everyone okay? This is typically how I'm going to start. I'm going to write the cosine of theta is going to be the dot product of G and H over magnitude of G times magnitude of H. So I'm gonna flash back to like the very beginning of the course where you have a formula here that you would like to just put numbers into. Do we agree that the three parts of this formula on the right side, the G dot H and the magnitude G and magnitude H, those are all calculations that might be useful to do as an aside, get them in their final form, and then plop them back over here. We don't want to do all the rough work here, or else it's going to get too yucky looking over here. So I'm going to do an aside, and we're going to find three things in the aside. Let's start with the dot product. So the dot product, G dot H, is, again, it's G1 H1 plus G2 H2. But at this point, do I need to write that, or can I just go into number form? Like first times first plus second times second. So I'm going to go right to number crunch. And that's why I didn't, when I wrote the formula here, I didn't just go G1 H1 plus G2 H2, because I know in my head that this is going to just turn into this. Trying to save me some pencil lead, okay? So I'm doing the x coordinates multiplied plus the y coordinates multiplied. So what's the x's multiplied? 5 and negative 3. And the y's multiplied are 1 and 8. So I end up with negative 15 plus 8 is negative 7. So from yesterday, I already know that my angle is going to be What does the negative result of dot product tell us? It's going to be obtuse. Okay, so that's what the sign of the dot product is your clue about what the angle will be. Acute, right, or obtuse, positive, 0, negative. Okay, so great. I also need, so I now know what the numerator will be. I now need the magnitude of G and the magnitude of H. So we calculated that before. To find magnitude of a vector in Cartesian form, remember it's adjusted Pythagorean theorem. Okay, so square root of the first coordinate of vector G squared plus second coordinate of vector G squared. Can we just, I don't want a decimal, guys, just write me this in as simple radical form as you can get. I'd even say right now, don't worry about mixed radicals in this context. So just tell me what this one is. What would be 5 squared plus 1 squared? 26. That one I can't make mixed anyway, but at the end of the day, if the goal is to find theta, it doesn't really matter if this is a mixed radical, so I'm just going to leave it as the radical that I end up with. And then magnitude of H will be the square root of, so I'm going to write something here and I want you to understand why this isn't going to work. What's wrong with what I've just written? Anytime that you're putting a base of a negative, you need the brackets. Even if you know that the negative 3 squared, you're going to get 9, technically you just wrote negative 9 on your paper, right? So anytime the base, the A or the B, is a negative, you need to put it in brackets. If you want to just put it in brackets all the time, you can, but you only really have to for negative numbers. So what do we get here, guys? Square root of 9 plus 64. 64 plus 9 is 73. Okay. Have we found the 3 pieces we need to plug into our formula? Cos theta is negative 7 over root 26. I'm going to put a dot. Okay. You don't want to even put a dot. I'll just put it next to it. 73. If you want, you can put them in like brackets like that. Oh, hello.
Sir, how are you?
What's up?
Good.
Sorry, miss. Who else was in the home class? Very well done. I really, last song was superb.
Really?
I didn't know it was Stevie Wonder. I'm sorry, miss. I didn't know it was Stevie Wonder because I'm not a Stevie Wonder fan. Mr. Sharp knows that too. I found that going through my stuff.
It's okay. Oh,
I
okay.
figured you had it, but I thought I'm going to give it to you anyways that
Okay.
way.
Okay, thank you.
Yeah, you all right?
You didn't feel like doing some extra math questions for homework, sir?
Thanks, man.
Bye, sir.
Okay. So I put everything together there. Is it now just find theta? So if I find theta, so you guys all know what you're doing now. You're going cos inverse. I'm not going to even write the cos inverse step. If you have cos theta is this, and the next thing you have is your answer, I'm fine with it. You're good with it. But the key there here is you guys it's really important you keep things packaged correctly here or else you're going to get the wrong answer. So grab your calculator. Let's make sure we're all doing this correctly. So negative 7 divided by bracket. I put the extra brackets here. I'm going to, this is correct, but you don't even need, if you wrote just the 2 radicals next to each other, it's understood that they're being multiplied. But you can put the brackets or not put the brackets, but when I'm typing it in, okay, I was going to put a dot, but then I was like, I don't want to confuse you about dot product. Do you guys get, it's understood based on what's on either side if the dot means dot product or the dot means multiply. In this case, if I put a dot, no one should be really confused that it's the dot product because the left and right, these aren't vectors, these are just numbers. So this is just a plain old multiplication. Okay? So the reason why I want to just be very careful here, because if you go negative 7 divided by, and you just start going negative 7 divided by root 76 times root 73, do you get that your calculator might not take that as it should be? You need to group the root 26 and root 23. So I'm writing in my calculator negative 7 divided by open bracket root 26 times root 73 close bracket equals, and then inverse cosine. I just got 99 degrees. Did you get 99 degrees? We are good. And confirmation about the whole obtuse. So that's a nice, like, double check for yourself. So, without you having to do any graphing of any vectors, you found the angle between those two vectors. Okay? Okay. Moving along. Okay, let's do it. Let's try it one more time. So we did it once, now we're going to do it one more time. So, cos theta is going to equal, this time it's not vector g and h, now it's vectors s and t. So s dotted with t over magnitude of s times magnitude of t. I'm going to press pause on my video for a minute, and I want you to try and repeat the process on your own to make sure you know how you're doing. So I'm going to press pause for a minute. If you're at home right now doing this, try and do this on your own, and then we're going to take it up in a minute. Okay? Okay. So we quickly discover when we do this. So if I start the aside, start with finding s dot t. So I have negative 3 times 4 plus 6 times 2. Negative 12 plus 12 is 0. I don't really need to continue to find the magnitude of s and magnitude of t, because now I know that the right side is just going to be 0. 0 over a number is 0. So I know I have cos theta equals 0. Automatically theta is 90 degrees. So again, that's one of those things that we talked a little bit about yesterday, but I'll stress it again, that if the dot product is 0, it's telling you your vectors are perpendicular. Okay, and figuring out if vectors are perpendicular is very important. Okay, and for other contexts of this type of mathematics. So far so good. Okay, let's move along. Okay, before I start talking about this next topic, I'm going to say, give it a chance. Okay. It's not as bad as it looks. I'm going to try my best to explain it. So, the title is Vector Projections. So, when you think of a projection, okay, like right now, I'm doing in class, you've been in my classroom all semester, and every day I've been projecting an image onto a screen, okay? So, there's some sort of relationship angle-wise, right, and direction of light and all this stuff that's taking something that's a small image there, making it big here, and all this kind of stuff, right? So there's a projection is a way of taking an image of something and putting it onto something else. So when we think of a vector projection, think of it like a shadow. So when you draw a vector, so here's a picture of a vector v, okay? And I want you to understand something. The only thing that's really in this picture is the vector v with a dotted line with the horizontal and theta. Everything else in this picture is not really there. It's more just, it's a consequence of the vector being there. So if you have this vector that's at an angle to a horizontal or to another vector, in this case u, okay? If we want to figure out what the projection of v onto u is, okay, think of it like there's light coming from directly from above, shining on top of vector v. Okay, the ground is in the direction of vector u. Do you guys see that a shadow is going to be projected on the ground in the same direction as vector u? Have you guys I'm sure you've all noticed at some point you're walking, and you see your shadow trailing behind you or in front of you. And that's a projection of the light onto you and forming a shadow. So think of it more like the light's above, okay? And something's leaning, leaning in at an angle. So there's going to be a flat on the ground version of that object, and that's called the vector projection. Okay? So the idea here is if the angle between vector v and vector u is acute, okay, okay, less than 90, then the projection of the vector v onto the vector u is going to be the vector component of v in the direction of u. So here's the symbol we're going to be using here, projection, proj, okay, P-R-O-J, okay. We do a subscript vector, and then regular size vector. So the way you read that is the projection of vector v onto u. That's what this is saying, the projection of vector v onto u. It's going to be the component of vector v, okay, in the direction of vector u that would make a 90-degree angle. So the main idea here is you drop a perpendicular to the shadow location, okay? You drop a perpendicular there. You draw a vector from the start of vector v to that dropped perpendicular. You just found the vector projection of vector v onto u. We'll do some practice ones, so don't worry so much. Okay, we're going to practice it to see how it looks in practice. But the one thing to mention before we go to that is if the angle's obtuse, okay, then do you see that the projection still happens? So we can't project it onto u, but we can project it onto a line that's opposite of vector u. So if it's saying, hey, I want you to drop a perpendicular to this vector. Well, I can't if it's pointing in this direction, but if I extend a dotted line, okay, do you guys get that? I drop this perpendicular to it. You guys see, I now have this shadow vector here that is the vector projection of v onto u. It's going to go in the opposite direction of u, but it's still on, it's parallel to vector u, right? It's not the same direction, it's opposite. Okay. And then if it just so happens that the vector v is perpendicular to vector u, then the vector v casts no shadow, and so the projection would be 0. So this is typically what happens if I stood like right under a light, and I said, look at my vector projection, you'd see nothing, right? There's no shadow, because and think of it, if you're walking around and the sun it's like noon and the sun's like right above you, you don't really get shadows if the sun is right above you. As soon as the sun, changes its direction, now the vector angle has changed, and that's why you end up with the projections going in different directions, like being visible and longer or shorter, that kind of thing. So, again, the best thing to do, I know right now you're probably like, this is weird. Okay, I get it. I think it's weird too, so when I first learned about this. But it's not as hard as it looks. There's a formula, use the formula to do. Okay? So let's link this geometric concept to an algebraic expression. So if I want to find the projection of vector v onto vector u, if 0 is less than theta is less than 90. So here we're gonna develop a formula right now. So we want to project vector v onto vector u. So the first thing we need is to create the endpoint of the shadow. So how did I say you're going to create that endpoint? You're going to go to the tip of the vector v. So here's the tip of vector v. Okay. I want to project that tip onto vector u. I make the projection by dropping a perpendicular to vector u. So vector u is on an angle here, so we have to kind of eyeball it to the best of our ability to make a right angle happen. And this point right here is the end point of the projection I want. So now, if I start at the tail of vector v, and I go along vector u until I hit that point, this little red vector I just created is the projection, okay, of v onto vector u. I just have drawn it. And now the goal is, can you tell me what that is related to the vectors in this question? So I want what that vector length is and direction. Well, the direction's easy. The direction, okay, is in the same direction as vector u. So the problem is the magnitude part, right? So let's think about this. How am I going to figure out that length? Well, it is a rectangular component, agreed? Rectangular component of because I've created a 90-degree angle. Okay, if I want to find the length of this vector here, okay, I want to find the length of the from A to the end point here. How can I go about doing that? Well, it is the horizontal. I'm not going to say horizontal. It's the horizontal. That's not the right word. It's, you guys get, because it's all skewed. I can't really say horizontal. This was all skewed back. If AB was horizontal, then I'd be saying horizontal. It's the, I want to find the length of this vector. How would I relate the information I have to find that length? I want to find the length of the projection of V onto U. If I know this length, let's say you know that length and you know that angle theta. Yep. Yep, SOHCAHTOA, you see it's a right triangle, right? Which ratio relates this angle and the vector, the length of vector V and the length of projection of V onto U? Cosine. So cosine theta is equal to adjacent, I'm going to write projection, okay? I know it's like a tedious symbol, but I want you to get used to it because that's the way you know you're finding the correct length. The length of the projection of V onto U over the magnitude of vector V. Okay, so the magnitude of the projection of V onto U is going to be, if I isolate that, what happens with the cos theta? It gets multiplied by, if I isolate the projection of V onto U, where should this go? Beside cos theta? Yep. Okay. I want you to understand that right now, you now have found the length of the projection. If you know theta and you know vector V, the number that results in a number. These are all just numbers. But I now have the value of how long that vector is. So we actually have a special name for this. This is called the scalar projection of V onto U. If all you care about is the length of the shadow, you're done. This is the length of the shadow. Okay? You take the length of your vector, you times it by cosine angle, ta-da, you have the length of the shadow on vector U. If I want to find the vector version of this, I want my vector to be this long, but I want it to go in the same direction as vector U. So how can I turn this into a vector? Well, let's think about this. So how can I turn this into a vector? Okay, so right now, let's just go through this. So vector U I'm going to just get rid of the projection part. Okay, so I'm going to get rid of this. So vector U has its own magnitude direction. Do we agree that magnitude of U has no bearing on the length of the shadow? Who cares? The length of the shadow is all based on the size of vector V. But what does matter, if I want my vector to go in the same direction as vector U, how have we in the course written vectors that go in the same direction as other vectors? We've written them as what operation did we learn that relates to writing vectors in the same or opposite direction of another vector? You think of the operations we learned even back in the last unit. If I have a vector and I want a vector that goes in the exact same direction but has a different size. Scalar multiplication. Okay. Do you guys get that? All I need is, do we all agree that this projection is going in the same direction of U? It's a scalar multiple of U. I just need to have the right multiple. I need to pick the right number. Okay? Well, right now, I can't just throw this number, okay, onto next to vector U and say I'm done. Okay? You know what, this might help. Maybe before we go any further, do you guys want to do a numerical one? And we'll go kind of do numerical and we'll go back to the rules. Okay? So let's go back to this. So I think this might help. So looking at A, let's do exactly what we just did in this generic example to find the scalar projection. We're going to find the scalar projection first. So we want to do, now, of course, I'm going to throw us all off here. I want to project U onto V. Do you guys get that? It means it's the other way around. U onto V. So here's vector U. Here's vector V. I want to project this vector U onto vector V. I have to drop a perpendicular to vector V. Is there enough space for me to do that right now? Like, is the given vector V long enough for me to attach a perpendicular? Can I extend vector V's line, though, so that I can at least have a place to aim? Yeah. So, this is what you do if you don't have enough space for your projection. You just extend your vector. So extend your vector, linear, okay? And now I have a place to aim for my perpendicular. So that I can draw my projection. So this would be the red vector I have just drawn. Let's see if we've been paying attention. Projection of, what should be the subscript vector this time? The little vector should be projection of, it's onto V. Whatever it's onto, that's the subscript. So this is the projection of U onto V. There it is. If I want the magnitude of that, okay, I want the magnitude, it's going to be the magnitude of big vector. I know this seems silly, but it's the way I memorize it too, right? So whatever the projection is, whatever the size of the vector you're projecting, you are projecting, that's the size you want. You want that vector cosine angle between. Oh, we'll do cos theta. So number cos angle. Do you have the number? Do you know the length of vector U? The length of vector U is 5. Cos theta, cosine 50 degrees. Okay, I'm going to get a number here. 5 cosine 50. 5 cosine 50 is 3 point, I'm going to go 2 decimal places, 3.21. Does that seem legit with the picture there? Like, the length of this is 3.21 longer than the original. Yeah. Yeah. Okay. Because if that's vector 1, I'm just referring to that size. So that's correct. Again, do you recognize that the length of vector V was completely irrelevant to you finding the length of the scalar projection, right? It was all based on length of original vector and the angle. So now I know that the length of the red vector is 3.21. Well, in this case, look at vector, if I want to know how, like this vector, the red vector, the one nice thing about this case is the length of that vector is 1 unit long. Is it a pure just scalar multiple then? If I have a 1 unit long vector V, and I want my vector to be 3.21 units long, in the same direction as vector V, then don't I just have to multiply vector V by 3.21 and ta-da, I got it, right? So the projection, so I'm dropping the bars, okay, and I'm just going to write 3.21 vector V. Is that an accurate description of the red vector? Yeah? Like, so if vector V in this specific example is 1 unit long, then a vector, I want a vector that's in that same direction but 3.21 units long. Isn't that exactly what this red vector is? It's going in the same direction as vector V, but it's 3.21 units longer than it. So therefore, it will be the length of the shadow and the correct direction. So this is the actual, and we call this the vector projection, because it actually is a vector. This is a scalar projection because it's the length of it. This is the vector projection because it includes the vector. Okay, this worked out so beautifully because the length of the vector you projected on was only 1 unit long. Right? You guys get, it doesn't have to be. Could that have been 2 units long, 5 units long? You know, it could have been any units long. Remember, vector v, it doesn't have to be 1 unit long for you to be able to do this. So, how can I guarantee? Do you guys get it? It makes life is so much easier if it is 1 unit long. Then it's literally like take this and multiply it. Just take this and multiply it by the length of vector v if it's 1 unit long. Way back at the very beginning of this of 7.1, okay, we talked about something called unit vectors, okay, and a unit vector in the same direction as a vector. Remember, it's like you have to. If you guys remember the rule for that, let's refresh our memory. So unit. What is a unit vector? Okay, if I have a vector. Let's see. If you remember, if I want to have a unit vector, unit vector, I'm going to say in same direction as, I'm just going to pick in this case, I'm going to say as vector u. If I want to write a unit vector in the same direction as vector u. Right now, vector u, I have no idea how long it is. It's magnitude of vector u units long. If I want that to be 1 unit long, does anyone remember the formula we used to find that unit vector? Okay. I know it may seem a little overwhelming. So let's go back for a second to. Okay. Let me go back. Okay, let's go look at this example in just a slightly different way. What if that vector had magnitude 2? Do we agree then this would be wrong? If that vector v had a length of 2, wouldn't this vector be wrong? Because now technically this vector would then be 6.42 units long. Because if you take a 3.21 and multiply it by a vector that's 2 units long, it's going to double in length, right? It won't be the right length to be correct. I want to always be able to take this projection and multiply it by a 1 unit long vector. Well, if vector v equaled 2 units long, what would be a vector that's in the same direction but only 1 unit long? So if vector v, let's think about this. So I'm just temporary. Don't put your pencils down. I just want you to think about this. If vector v's magnitude was 2, okay, how could I make vector v have a 1 unit long? I want it to be only 1 unit long. What would I have to do as an adjustment to vector v to make it only a 1 unit long vector? Divide by 2, or more specifically, times by a scalar of a half. Okay? Do we all agree that's equivalent? Just even think, they're just balancing an equation. Okay. If the vector, so whatever the magnitude is, if you want to have a 1 unit long vector, and let me just pick a number, let's say it's k, random value, right? Random value k. Okay? If whatever number is here, okay? Do you guys see that in general, whatever number is there, that's the number you would have to multiply by to be able to get a 1 unit long vector, right? Depending on what number is here, 2k, whatever, 1 over that number will give you a 1 unit long vector. So going back to this question then, if I want a 1 unit long vector, and I know right now this vector has a magnitude of u, okay, as its length, how do I make it have a magnitude of 1? 1 over magnitude of u times vector u. Does that ring a bell? The magnitude of u is the length of vector u. If you take the vector u and multiply it by 1 over its length, have you just created a vector that's 1 unit long? Maybe? Okay. If vector u is 10 units long, then won't 1 over 10 vector u be a vector that's 1 unit long? If vector u is 100 units long, then won't the vector 1 over 100 vector u be a vector that's 1 unit long? So this is a general rule, okay, that will be the unit vectors in the same direction as vector u. So that being said, if I multiply this by this, won't I be getting the vector projection of vector u, of vector v onto u? So what I mean by that is, so this, think of this as separate, okay? If I just want the projection of vector v onto u, it's going to be the scalar projection, okay, what I just found, the length of the projection times the unit vector in the same direction as vector u. So I need to write little labels here. Scalar projection and unit vector. Okay, let's think of it. Let's think logically. You know you want a vector that is this big. Projection of vector v and vector u. We don't want it to be that size. If I take that number and times it by a vector that's 1 unit long, will it have the right magnitude and the correct direction?
Yes.
If you, I'm going to say that one more time just to think logic. I want my vector to have this value, whatever this is, I want it to be this long. If I take this number, multiply it by a 1 unit long vector, won't that end up being the correct length and the correct direction? Because it'll be going in the right direction, vector u, and this together, this is going to be the correct magnitude. Now, this is where something kind of cool happens. If I put this actually together symbolically, you guys get what I just did there is I threw everything that's a number, I threw in front of the vector u. This is remember, projection of v onto u is a number. 1 and magnitude of vector u are numbers. So I have this in front of the vector u. Now, I'm going to do something a little funky, but hopefully you think it's kind of cool. Look at that. If you look at that numerator, is it super close to something that we've been talking about in this unit? The numerator. Magnitude of v cos theta. What's this lesson? What was the first thing we did in this lesson? We reviewed what rule? The dot product. Magnitude of v cos theta. Man, this is so close to being the dot product. What's the only thing that's missing?
The U, but it's right there.
Well, but it's in the wrong spot, right? We can't just be like, hey, let's move it up. We can't just like sneak it into the numerator, okay? We can't just sneak it into the party. But what we can do, it's just a number. Can't you do this, guys? Like it's like a common fraction, like equivalent fraction, multiplied top and bottom by magnitude of u. And now, you guys probably are, I'm going to write this, and you're going to like, you should have just told us this to start with. But this is, I'm basically going to tell you the formula. Here it is. What can you replace the numerator with? If you calculate this, you get the vector projection. Wasn't this so much more fun than me just telling you this formula? This is the vector projection. Yeah. Yeah.
So why do we want to bring it back to V1? Like, why do we want that?
Okay. So, if the goal is to find a correct description of this vector here. Okay. I know that the length of that vector is the magnitude, is this thing, right? Magnitude of v cos theta. I know that is the length of this vector. I can't just go times by u done, because what if vector u is already 15 units long or 100 units long?
Oh, okay.
Because if I just do that times vector u, then now it's going to be that many times bigger. But if I pick a 1 unit, right? If I go, I want this little 1 unit long vector. It's in the same direction as u, but just 1 unit long. And think of it like you just built DIY unit vector. You know how we did I and j? Those were the ones in the x and y direction. You just found a 1 unit long vector in the u direction. And if you have a 1 unit long vector and you times it by this, then you have the correct length and the correct direction. Because you just put the correct scalar multiple to a 1 unit long vector, you'll get it. So take a look at that last formula, because that's the one you would need to use. Okay? So if you're asked to do a scalar projection of v onto u, dot product of the vectors, and then for the vector projection, the other calculation you need the length of vector u. It works out in this case, you have to square it. Okay? And then that number in front of vector u will give you the correct length. So, okay, that is the correct solution. So let's go back to the pictures. So go back to example 1, or example 3, I should say. So we did everything we needed to do to get the projection here. It was easy. We didn't have to do any adjustment because vector v was already 1 unit long. So in A, we were all good to go. Let's see what happens in B. So we're going to project P onto Q. So you have to always set that in your brain. What's being projected onto what? So where's the shadow going? Is the shadow going on P or Q? Onto Q. So Q is your shadow place. Okay? So I want to drop the tip or the head of vector P onto vector Q. Is it good to go, or do I need to do any extension here? Because here's vector P. Is it going to actually lie on the drawn vector Q here, or is it actually on the other side there? So I need to kind of extend a reference line so that when I drop my perpendicular, okay, here's my little vector. You have just, this right here is the projection. Let's practice. So what's the tiny vector and what's the big vector here? Projection of what big vector, so what big vector onto what little vector? P onto Q, so the subscript vector is at P or Q, the subscript. Q. So projection of vector P onto Q is that red vector there. That is what we need to figure out. Let's find the length of it. So the projection, okay, of let's see. Q, P onto Q. Okay, this one's easy. It's just magnitude, okay, the length of vector P times cosine angle between. Okay. Something a little interesting happens here, but we'll embrace it. So what's the magnitude? Let me just do angle here. Magnitude of vector P cosine 120. What's the magnitude of vector P here, guys? 20. Oh, I didn't mean to do that. That's what I meant. 120. So there's your formula for scalar projection. I throw in the length of vector P and the angle between the vectors. And I do 20 cosine 120. And I get negative 10. And you might be slightly freaked out, because what's the one thing we've said about magnitudes? It can only be positive. And are we slightly disobeying that rule at the moment? But technically, another way of saying this is 10 in opposite direction, right? It's kind of giving you that extra little piece of information. So 10 in opposite direction of Q. Okay, so really the projection should be 10, and the negative's telling you the fact that it's going in the opposite direction of vector Q. All right. And you guys don't like this part, because now we're just going to go formula. Okay? So I want the projection, okay, of P onto Q. I want you to kind of see the pattern here. This is our general formula. Okay? For the vector projection, this is the way I memorize it. It's a little bit cheesy. This is the way I memorize it. You got to see that one vector is the vector that shows up the most in this formula. Okay? There's U's and V's. V only shows up once. U is everywhere. So I want you to look at your symbols over here. What's the vector that shows up the most in the vector projection? The vector you're projecting onto, the U. Okay? So the subscript vector. That's the subscript vector is the vector that needs to show up in your vector projection formula. So in our case over here, what's the small vector Q? You guys get, that's the vector that shows up everywhere. So P gets its one little moment in the sun spotlight in the numerator in the dot product. Then everywhere else it's Q's, Q's, Q's. Okay? If you literally just plug in, okay, the dot product of P and Q and the magnitude of Q squared into this, and you put that number in front of vector Q, you're done. So now you see it's more of just a formulaic thing. Find the dot product, find magnitude of Q squared, plug it in, ta-da. So let's do that. So do a little aside. So P dot Q. So again, you have your two options. You can go algebraic or geometric, but based on this scenario, what's the more appropriate choice? If you're given a picture, we should choose the geometric. So magnitude of P times magnitude of Q, cosine angle between. In the picture, do you have the magnitude of P? Magnitude of P is 20. Magnitude of Q is 30. Cosine angle between 120. 20 times 30 times cosine 120. 20 times 30 times cosine 120 is negative 300. So negative 300. Okay, I'm like, is this painful? I didn't even hear you. Okay. So negative 300. Did you hold it in? That's what I heard. No. Okay, I didn't hear. Okay. So magnitude of Q squared is not just, you just have the magnitude of Q. It's through 30 squared. Okay. And then just leave vector Q next to it, because the goal is your answer is a scalar multiple of that vector Q. What's negative 300? What's 30? Another way of saying 30 squared, it's just 30 times 30. Oh my gosh. 3 times 3? 9. And then put 2 zeros. Oh my god. Okay. Okay. Almost done.
Yay.
What's this? Don't leave it like this. You'll make me very sad.
I wrote it 2 reasons I'm squared.
Negative. How many 300s fit into 900s? Oh my gosh, I'm going to pretend you all know that that would be the reduced form of 300 over 900. Okay. I want you, again.
I was so close.
Yeah, I know, right? Okay. Take a look. Does that actually seem legit? 1, 2, 3. You guys see what I'm saying? I'm going to draw that again because you weren't watching. Watch. Eyeballs. forward, eyeballs. See my little projection? 1, 2, 3 in the opposite direction. So a third in the opposite direction is the correct projection. Okay. Now, what if you're given the algebraic form? Okay. And here's the deal. So I started with the scalar projection. If it doesn't say the word scalar, I'm going to say assume they want just the vector projection. So if in C, I want the projection of D onto C. Let's just do the vector projection this time. So let's do this. We can do this in 3 minutes. I have faith in us. Okay. Vector, so if I want to find the projection of D onto C, what's the subscript vector? C. C, senors and senoritas. Okay.
Culture.
Spanish. Hello.
C, like, yes. So, okay. So, let's see if we can do that formula, guys. Left something? Okay. So what's that fun formula? There's a dot product on the top. Here's the cool thing about dot product. Who cares about the order? Tell me the dot product with those two vectors. C dot D. Okay, so now my question to you is, what's the vector that shows up everywhere else? Is it D or C? C. See, the little subscript gets to shine its little light on the world here. Okay? Okay, so in this case, I need to do a bit of work because I don't have a picture to just grab magnitudes and things. I need to find some stuff. So let's first find, this is my find stuff aside. Can I find C, vector C dotted with vector D? In this case, what form should I pick? Algebraic. Woo! Okay. So 2 first coordinate times first coordinate plus second coordinate times second coordinate. What's the magic number here, guys? 2 minus 12 is correct. I need magnitude of C. Oh, they just gave me the vector, but can I find that length? I feel like it's a game show. Find that magnitude. Okay, let's do it. Can I find the magnitude of C? Square root of first coordinate, second coordinate. So 1 squared plus 4 squared is the magic number. Who's going to win the game show here? 17? Okay. But wait a second. When I put it over here, it's squared. So just 17.
Oh, whoa. Look at that.
Negative 10 over 17. Now, here's the one little new fun fact here. Because vector C literally has an algebraic form, we can replace the vector C as well. And then if you remember when we first did this, we can scalar multiple both of those pieces. So what would the final pièce de résistance be here? Negative 10/17 times 1. Negative 10/17 times 4. We did it!
No worries.
Do you really thank me for that? Okay.
Miss,
Come after school.
I can't.
Ask me on the weekend. I'll stay after school Monday. Okay, so we'll finish this off and start 7.4 on Monday. Do as much as you can. You should be able to do the majority of the homework, guys.
Can you go back? Can you go back?
Oh my gosh, where do I go back to? This?
Yay.
Don't post that or meme that.
Too late, already tweeted that.
And you didn't ask me if I wanted to show you the back.
Okay, I'll go to physics, but I'll do physics.
No, but I just wanted to show you where it comes from. Yeah,